Hi, this is Tony from College. So far, we worked with one equation at a time. What we did is that we solved it in order to find the value of the variable or variables in that equation. We were able to describe one general rule with that single equation and then apply this rule to a series of cases. Now what we're going to do is to look simultaneously at two equations. This will allow us to move beyond what we did so far, i.e. simply describing a series of cases that obey to the same rule, to be able to compare these cases when they are subject to different rules. I know it's a mouthful, but bear with me. We're going to take concrete examples and it should become clearer. For instance, we had this general rule for a cab driver that we expressed with an equation that looked like this. And we were able to figure out the prices for different distances. All right, that's neat, but we can do more than that. Many times in real life, we want to compare different options in order to choose one. We can use algebraic equations to do exactly that. So now let's bring a second driver that charges according to a different rule. So here is the rule for the second driver expressed in text. Try to pause the video and write the equation that corresponds to it. All right, let's do it together and see if you got it right. So we are looking for the price, so we put P alone on one side. This P, this price, is determined by two components. One is fixed and the other one varies with the distance traveled. The fixed cost, the base fee, is 6. This 6 corresponds to 3.50 that we have with the first equation. Now we need to add the component that varies, and that component is the $2.50 that changes according to distance. The distance expressed in miles. So that D is multiplied by 2.50. All right, let's give a name to these two drivers so we can keep track of what we are doing. Here we have our two equations, and let's say the first driver is called Sheldon, and the second one is Leonard. Now you want to decide whose service to use, and your goal is to get the cheapest ride. Now that we have two examples in front of us, let's just bring back quickly the one equation versus the two equations thing. So with one equation in earlier videos, we were describing a series of cases that obeyed to the same rule, right? We had this cab driver here, and we calculated the price for 5 miles, 3 miles, 7 miles, whatever. Now what we're going to do is take a distance again of 3 miles, 5 miles, 7 miles, whatever, and plug this distance into the two different equations and compare them. So with two equations, we can compare a series of cases when different rules apply to them, right? Here, there's going to be one rule for Sheldon and another one for Leonard. They charge according to different equations, different models, different rules, whatever you want to call them. For any given distance that you travel, you have three possible scenarios. 1, Sheldon is cheaper. 2, Leonard is cheaper. Or 3, they charge the same. Let's say you want to take a 7-mile ride. As we did in previous videos, we're just going to plug in the number. So meaning here we have to substitute D by the number 7. This is what we get. And we find out that the price for a 7-mile ride with Sheldon is $24.50. Now let's see how much Leonard charges for the same distance. So again, we substitute D by the number 7 and we get a price of $23.50. So Leonard is cheaper. You should ride with Leonard. You would save $1 compared to riding with Sheldon. So what we did is figure out who is cheaper for a single case. Here we took a distance of 7 miles. This is pretty neat because you can make a decision now if you want to take a ride for 7 miles. But you don't want to do the math every time you need a cab. In the next video, we will see how to identify which driver to call for any distance, not just for one case.